So homework check tomorrow, and we're gonna update our formula sheets to the final. Goodbye, my dears. Have a wonderful Tuesday. Bye, guys. Thanks for being wonderful. Bye. Thanks, Jacqueline. Bye, bye, bye. All right, so guys, I think I told you yesterday I'm not using the 2.6
Good
notes.
morning, Countryside High School teachers. Pardon this interruption. Teachers, at this time, if you will please reference the email sent by Mr. Bernstein this morning regarding college dual enrollment. Please send those students at this time, only those students, to the media center. Thank you so much.
This is notes and homework right here. But what this, guys, this little note for you. So I have lots of notes for you. Okay, you took one, you put your phones up, right? I'm checking. You can, if you want to lighten your notebook a little bit, not mandatory, of course, but if you want to take these pages out, waste of paper, don't yell at me. We're not going to use Gene Patterson's 2.6. We're using Brian Passwater's 2.6. These are the two bigwigs in the AP Pre-Calc world that make all of our curriculum. But, you know, I keep saying she all the time, like she. Jean Patterson creates all of our stuff. She's wonderful, but she goes too in-depth sometimes. That's why you see me skipping things. 2.6 is a miss. So Brian Passwater is my other go-to, and I loved this section. You guys will probably like it, too. I think it's pretty easy. And it is also more like conceptual than like doing arithmetic, okay? There's really not a ton of math. It's just kind of like understanding things, okay? Then don't forget tomorrow is a work day. Great day for you guys to catch up on any homeworks, watch the videos if you weren't here, homeworks if you weren't here. I'll release the key to the quiz. I'll just let it show you answers maybe after this class period. So you can go in and see what you got wrong. And guys, be smart. Use tomorrow to your benefit. Go back over, because there's a homework check at the end. Go back through all your homeworks. Did I finish everything? Oh, wait, what was that assignment? Let me go in Canvas and see. Okay, all my homeworks are caught up. I have no questions for her. Let me go back and look at my quizzes. Maybe I have some questions on what I got wrong there. So just think, what do I need to do? What can I ask her? Because I am at your beck and call on these work days. I end up just doing other things because I feel like I'm bothering you. I walk around. I'm like, you need help? You need help? So please don't ever be shy about asking me to help you. I would rather do math with you guys than anything else. I'm bored when I don't get to teach. So please, 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 use tomorrow. Think, what can I use that time for to best support me, okay? Meaning you. Okay, so everybody's here. I love that. I love it when that happens. Okay, so, and then, so let's talk about the rest of the next, 10 days or whatever. So 2.6 day, just one day. You should probably finish your homework in class. Tomorrow's the work day, like I said. Then Thursday, we're actually going to do like a little group activity as a review, something just a little different than our normal stuff, just to kind of take a pause, again, review exponential functions one more time. Then we go on to our very last section. 2.7 is on Friday and Monday, and that's it for this new material. Then we have 2 days of test review, Tuesday, Wednesday, and then the test next Thursday, Friday, on 2.1 to 2.7. Okay? At that point, we are halfway through all the material in this course. Pretty crazy. At that point. So you're one section away, basically, or two, if you count this one, from being halfway through all of the content. So that's pretty amazing. Okay. So, okay, so Aaliyah's question is about the fourth unit. Great that you remember that. There's 4 units to the course. 1, 2, 3, 4, you can see it on there, or your course civic lit. The 4th unit is not on the AP exam. I'm not even going to look at it until I'm not touching it until after the AP exam. I don't even have it in my brain how much time is in between the AP exam and the end of the year. There are a few topics in there I would love to cover, but yes, it would be very light. It would be very, very, very light. So one of the things we're going to talk about second semester, besides, of course, getting ready for the AP exam, is you guys that are sophomores or juniors still have to pick a math class for next year. What are you going to decide to do? So that's one of the things I'll be helping you with. For those of you deciding to go to AP Calc, you have 2 choices. You have A, B, or BC. I've had kids jump right from pre-calc to BC and be successful. And we'll talk more about that another time. But there's some concepts that I usually cover in regular pre-calc, honors pre-calc in the past, that you need to know for BC that are in that unit 4. So I have to kind of decide what I want to do. One of the options is for some of you that are super motivated that want to go to BC, because you can get credit for A, B, and BC on the exam. It's a whole thing I'll talk about another time. But if you want to do that, there might be some summer work for you to do to be not behind the other kids. So, but we'll talk about that. But I think I did say AB, you guys would be so prepared for AB. It's just, I'm so excited about you guys taking it next year. Okay, so we'll talk about that another day. So let me read. There's nothing to do on this page except just kind of pay attention to the concept. So just give me your record. Give me your attention while I. Okay, well, it's all recording. All right. So throughout this course, we'll have many opportunities to work with and create models based on a given data set. 3 particular important examples of this are linear, quadratic, and exponential models. Because these 3 types of models occur frequently in the real world, there's a heightened focus on them in AP Calculus. So we've done a bunch of stuff with linears, quadratics, and we've been really focused on exponentials the last 2 weeks. On the AP exam, students will be expected to determine which model is most appropriate given a set of data. There are a few strategies and methods that we can use to determine whether a linear, quadratic, or exponential model is most appropriate for a given data set. So understand these words. I think you guys know linear, quadratic, exponential. We're going to break that down even more. But model. A model is an equation, like a function that you can plug numbers into. Many of them we've worked with the last few days, where they give you like a formula that computes how the half-life of some bacteria, whatever. That equation they give us is a model. And we plug in this or that. Yesterday we had one about pressurized cabin or pressurized air or air pressure, depending on height. They gave us that equation with the e to the power of blah, blah, blah. That was a model, okay? We use models to predict what will happen when we're 10 miles or kilometers in the sky, or if there's 46 bacteria or whatever it may be, or time going by, okay? So linear, quadratic, exponential, I think we all know what the graph looks like. If we plot points, it looks linear, quadratic, or exponential, okay? These points, though, if you look a little closer, they're not exactly linear, we're not hitting every point right down the center for these 3, but generally they are, okay? So what these points are these XY charts, graph for us, and then a line of best fit, a regression is given. Like, it's mostly linear, right? Relatively every point is the same, a constant distance apart, okay? And when do we use a linear model? And that's when we have, this is that word, relatively constant rate of change. Like, if you had graphed this back in like algebra 1, even algebra 2, we would have been like, what's wrong with it? Something's wrong. Because lines, we should be hitting every point. They're exactly the same distance apart. But now we're talking about real world data. And nothing is very few times is it exactly perfect, right? It's what's the closest model to it, okay? So with linear, you're basically adding something that's like close to the same number as you go through the table, okay? And even though this is not exact, okay, especially when you look at it here, I have minus 2.6, when you plot the points, you can see visually it looks pretty linear, okay? An example of that is, let's pretend you work at Starbucks, okay? You get your hourly pay, and your boss gives a Christmas bonus every year, okay? So you get your hourly pay, you work there for a year, now you're at Christmas, and your boss is going to give you a bonus. He bases his bonuses to you guys on how well the store did that year. This year, everybody's getting a $200 bonus, okay? Next year, store didn't do so well. He's going to give everybody $150. And then the next year, ooh, we did really well. Everyone's getting $220. That's linear. Even though it's not the same amount each year, it's adding an amount. It's not like a percentage or anything like that, okay? Yeah, sometimes the numbers can go a little out of order, but we are adding a certain amount each time, okay? Your pay is going up. So quadratic, again, this is not a perfect parabola, okay? This is your quote-unquote vertex for 2.1, right? normally in a quadratic, the numbers on either side are exactly the same, right? This would be like 4 and 4 and 9 and 9. It's not exact, but it's close, especially when you plot the points, okay? In quadratic, that's probably the most common one we've done word problems with, which is like things that, like the ball that drops and bounces and goes back up, an arrow goes up in the sky and falls, or a dolphin jumps out of the water, hits its highest point, and so we can model quadratics pretty simply. We're pretty familiar with those. And we've been doing a ton of exponential. I mean, think of all the word problems we've done. So many of them, okay? And with an exponential model, the output values are roughly proportional. What the heck is proportional? So if I, go way back, literally 5th grade, I'm tutoring a kid in 5th grade, so I know. When you had to complete this, it's like cross multiplication. You guys wouldn't even take that time. You'd go 2 times 2 is 4, so 1 times 2 is 2. These are proportional. You're multiplying by the same thing each time, right? It's not always exact in real world, but especially when you see the graph, you can tell that this is modeling something exponential. One more concept to talk about before we go on. You all know what an ordered pair looks like. We've seen it so many different ways. Thanks, sweetie. X, Y, X, F of X. Don't forget, it's also, hi, thank you. It's input, output, and you don't have to write these. I just want you to understand, because they're talking about inputs and output. And in a minute, there's going to talk about independent, dependent. Okay? So it's important to kind of know when they throw these other terms out that we know what it's referring to. Okay? So X and Y, input, output, independent, dependent. Okay, so in our next group, guys, let's do this lightning fast. This is almost beneath you. Plotting points and saying, what does it look like? A line, a quadratic, an exponential. It's not going to be perfect, but you should see a line of best fit. Okay? And do not think of perfection. Let's get through this quickly because this is just too easy. You can try and connect them if you want, but really, can you predict what does that most closely represent? And that would be, of course, linear. Okay? We're going to do A, B, and C. Don't worry about D. I'll tell you what D is when we get to it. No reason to do a whole bunch of these. I tell you all the time I'm not into busy work. Somebody's phone is going crazy. Oh, you guys are all nervous now. So guys, even though B is, it doesn't look like a quadratic. It almost looks like an absolute value. That's not one of our choices. This is roughly quadratic. Okay? If I show you the key, this is done like digitally. It doesn't hit every point. Okay, it doesn't hit every point. But it's roughly a quadratic shape. You could it's modeling that behavior. And the last two, whether you do them or not, exponential, right? So we should be able to look at some points and decide which one of these it most closely represents, okay? This is not about perfection, so don't overthink this. You have a couple of these in your homework. Quick, easy, done, okay? All right, this is the new stuff down here. So this new word, this is brand new, okay? If you've taken AP Stats or Prob and Stat, they go really deep into residuals, really, really deep into it, okay? We don't. We're touching on it, just which is really kind of interesting in my opinion, in real life, applicable. But we're not going deep into it. But if you find yourself being like, oh, that's kind of interesting, or I like that more than some of the other stuff, maybe that tells you what you should take next year. I don't like that kind of math, but whatever. Okay, so listen, when we create a model, those equations, okay, that you can plug numbers into, we can use our model to predict. Models help us predict. Remember yesterday, air pressure, we had an equation and they wanted us to predict what the pressure would be at 10 kilometers. So we took 10 and plugged it in. And it gave us a prediction, not actual. It's a prediction, okay? When using a model, it is important to remember that this is only a predicted value. If we use the input, or x values, from a known data point to find a predicted output using our model, the difference between the actual output and our predicted output is called a residual. So let me put that in English. This is a formula we're going to need to know. Tomorrow, one of the things we're going to do is update our formula sheets finally, and I've added this to it. So you have actual data, and then you use your model to find predicted data. The difference between those is the residual, okay? It's a way of seeing the error in our predicted model, okay? So let me give you an example on this next page, okay? So listen closely. This is not difficult at all, but I think some people miss this part of it. The weight of newborn babies can be modeled by a linear function for the first 4 months after birth. Selected values for the weight in kilograms of a particular newborn baby are given in the table above. This is real data. This is a baby that's born. So the minute it's born, so no time has gone by, it weighs 3.2 kilograms. Yeah. Then after 1 month, its weight. 2nd month, 3rd month, 4th month. Okay? This is actual. That's the part I think my first period was missing. It says a particular newborn baby. This is not predicted. This is here real data. This is true information. Okay? What we're going to do is use our actual data to create a model that we can use to predict future months. Okay? So we've already done this. We did the same exact steps yesterday. Use the regression capabilities on your calculator to find, and it's going to tell you what model to use. Say use linear. And we're going to come up with a model. So remember how to do this. Clear your RAM, please. And just like yesterday, when we have points, not an equation, we go to stat enter. Remember your x values and your y values? So we just type those in. Make sure you hit enter so it's in the brain of the calculator. Sometimes we forget to hit enter after our last one, right? Then you go back to stat, over to calc again, and it told us to do linear. So we're going to go number 4. And I haven't looked ahead yet, let's say, to see if I need to store it. It's so quick to store something, so it almost, you might want to just make it part of your steps here. But, sometimes if we just want the equation, we don't really have to do this step, but it's good practice anyway. It doesn't hurt. Alpha, trace, enter. So in case you want to see the graph, look at the table, find an intersection, do anything else with it, it has to be in the brain of the calculator. And by doing that, it's in there. Okay? Again, if I just wanted this information, I could have skipped that step. It would still give me this. Right? So there it gives you the model, ax plus b, right? Slope-intercept form. Don't get hung up on a and m being different. It's still linear, x to the first power. So my model would be 0.8x plus 3.34. What? That's wrong. That's totally wrong. And you can tell by looking at your calculator. A is 0.8, so it goes in front of the F. B is 3.34. That's all. Okay. So we have a slope of 0.8, getting bigger, right? It's positive. That makes sense. Hopefully the baby's gaining weight. And look, this would be your y-intercept. 0 is 0, 3.34. The actual is off already, right? 0, 3.2. With the model, it's 3.34. This is used to predict. Okay? That's a huge concept. Noticing which one's actual, which one's your predictor. Okay? Because, and I say use to predict, because this is the model. Now I can plug any amount of months in and see what the weight could be. It's an educated guess. So use the model found in Part A to predict the weight in kilograms of this baby 2.5 months after birth. You can plug 2.5 in right there and simplify it with your calculator. You can use your table if you want to. You would just have to change your table to count by 0.5. It's very simple to do right from the screen. It says to press plus for change in table. So if I hit plus, it's saying, okay, right now it's counting by ones, right? 0, 1, 2. You hit 0.5, enter, and go down to 2.5. That's what you would get if you had done it algebraically. So it's good to know, more than one way of doing something. If we have to do it by hand, if we have to use our calculator, whatever, okay? So the model would be 5.34 kilograms. Is this predicted or actual? Predicted, okay? So you don't have to keep writing this. I'm just really trying to send it home, the difference between these two numbers. So Part C is the actual weight. They're giving us some more data. They're giving us some actual data. Just at the risk of being obnoxious, keep writing it. The actual weight of this baby, 2.5 months after birth, was 5.5 kilograms. What is the residual for this weight? Remember the formula. Residual is actual minus predicted. Alphabetical order, too. So actual is 5.5 minus our predicted, which was 5.34. In our calculator, we get 0.16 kilograms. Okay? This is called your residual. That leftover amount, the difference between the actual and the predicted. Okay? And this is an important part. This is stated in my stuff, the CED, that this is going to be on the AP exam, this next question. Did our model underestimate or overestimate the weight? So remember, actual, model. Did this guy underestimate or overestimate? Under, right? This is less than this. So if you get a positive answer, it's underestimated. Okay? So read the question. This is your model. Did it under or over? It's under, because it's less than that. Underestimated. Okay? One more concept. Okay? One more new concept. So a residual plot, that's actually a graph of all your residuals. So if we did this work, we don't have to, don't worry. If we did this work for like a whole bunch of ages, what was the actual, what was the predicted, subtract them. And you graphed those. That's called a residual plot. We don't have to do that, okay? That's not something we have to do in this class. That's going really deep. But we have to know what a residual plot tells us. So if we're handed a residual plot, which we will be on the next page, we can tell things by it, okay? So a residual plot shows all the residuals for a set of data that can be used to help determine if a model is appropriate for a given set of data. So this is a huge concept that is kind of confusing at first. If a model for a given set of data is appropriate, then the residual plot should appear without pattern. So if I made a residual plot of some data and I could see like a quadratic or a line or something in it, I would say that's not good. We want no pattern, okay? So let's see what that looks like. So here is an example of a residual plot. Again, don't worry about graphing it, how to graph it. We don't have to do that, okay? But what this is all those little 0.16s, all the different subtraction solutions plotted on a residual plot. This is like an x-axis. Some numbers are above the x-axis, positive or negative, okay? So we just have to look at that and say, does it look like a line? Does it look like a quadratic? Does it look like an exponential function? And the answer is no. So before I even read that question, I'm going to say to myself, there is no pattern going on here, okay? An exponential regression was used to model a data set. The residual plot for the exponential regression model is shown above, okay? Which of the following is the best conclusion about the appropriateness of the exponential regression based on the corresponding residual plot? So when there's no pattern, that's a positive thing. So we already know it can't be A or B because it says not appropriate. When there's no pattern, it's a good thing for our model. Okay, so that's opposite of what we normally think. The exponential model is appropriate because it shows no pattern or because it shows a pattern. Tricky, no pattern. No pattern is appropriate. All right. You might remember, we're almost done here, you might remember back in Unit 1, we had one problem, so I'm sure it might be fuzzy for you, where we were given some data and we had to decide, is it linear, is it quadratic, or is it cubic? So we put the data in and we would graph it and look at the picture, okay? And we would say, oh, it looks like a line, or oh, it looks like a quadratic, or oh, it looks like a curvy graph and it's cubic. So that's what happened here. So a group of AP Pre-Calc students used a set of data to create linear, quadratic, and exponential regression models. After creating the three models, the students created a residual plot. So that's what these are. Make sure you understand that. These are the residuals, not the actual regression. Two RE words, too, which makes it confusing. Based on the three residual plots above, which model is most appropriate for the data? And give a reason for your answer based on the residual plots above. So let's look at them. This one is linear, this one is quadratic, and this one is exponential. These are the residuals. These are those leftover points, like up here, okay? You don't want to see a pattern, right? I could easily see a pattern here. I could draw a line of best fit through these points, and I wouldn't even miss one, okay? That's kind of what you want to think of. Same with this one. This has a pattern. That says pattern, believe it or not. That's bad. This one has a pattern. We don't want that one either. This one does not show a pattern. One of the things we look for is like there's about the same number above as below. This is no pattern. This is the one that makes us happy. No pattern. So which regression do we want? We want the exponential one. Why? No pattern to the residual plot. So that's what we were deciding. Which one of these? The one with no pattern, that makes us happy. Okay. Mr. Passwater hopes to make it into the Guinness Book of World Records by painting the world's biggest mural on the sides of several downtown buildings. His mural will consist of many painted circles of various sizes, where each circle is painted a different color. He wants to create a model to determine how much paint is needed in quarts for a circle of radius r in feet. Should Mr. Passwater use linear, quadratic, or exponential model? Explain more. I didn't know what the answer to this one was at first. I mean, I had a key, and I was like, I'm not making the connection. And then when I researched it some more, it made a lot more sense. So we're talking about circles, and we have to choose whatever the model is. You don't have to find the model, but would it be linear, would it be quadratic, or exponential? Does anyone want to guess what you think? You said what? Linear? Anybody have a different guess? And when I tell you the answer, you're going to be, I hope, that oh, okay, makes sense. But it didn't make sense to me at first either. Yeah. Why quadratic? But that's the answer. Okay. What's the Do you remember the formula for area of a circle? Pi r squared. It's quadratic. That's why. Okay? That's why. Because the formula to find the area of a circle is a quadratic formula. Anything to the second power. So what if they were rectangles that he was painting? That's length times width. That's linear. And I don't know, I can't think of an exponential example. But quadratic pi r squared is a quadratic function. I don't know. Seems kind of dumb. Last question though. Should he overestimate the amount of paint or underestimate the amount of paint, and why? Real world, right? Does he want to go to the store and buy more than he might need or less than he might need? More, right? You want to overestimate. Why? Common sense. So he doesn't run out of paint. Okay, so some of this is just conceptual. There's no like math. It's just kind of reasoning. I'm much better with give me a formula, plug some numbers in, good. But that's what we had to know from it. Okay, so we're going to work on the homework. I'm here for you. Please just try to get through it and ask me if you don't understand my key. All right, so I can try and explain it to you better. There's not much to this lesson. Pretty straightforward. So the homework should match this pretty well. Okay, now, when you get to the homework, guys, the first few, don't spend a lot of time on those dumb graphs. It's beneath you. It's beneath you. Okay? Just make it quick. Okay? I'd rather you get to the conceptual stuff. I know you guys know how to plot points and tell if it's linear, quadratic, or whatever. The other one is exponential. Yeah. Mm-hmm. (168 through 183). Anything that's 2.6 you can get rid of. Your next page should be 2.7. I think there's a leftover on the other side. But,